everyone. The title of my thesis is Optimization of Parallel K-Means Clustering Algorithm, based on Cloud Computing Platform Hadoop. The thesis mainly involves the following contents. Introduction: Parallel KM TSAR optimization based on Parallel KM TSAR optimization experiment based on optimization experiment analysis of Parallel KM TSAR based on conclusions. 1. Introduction. In recent years, with the rapid development of the Internet has accumulated a large amount of data. The traditional operation of data mining algorithms is mostly run on a single machine. When processing these large-scale data sets and high-dimensional data types, due to the limited resources such as CPU, GPU, and memory of the single machine, it can no longer be quickly and accurately qualified for data mining tasks. 1-2. Combining cloud computing technology. Deploying data mining algorithms in parallel to clusters and using multiple machines to quickly execute data mining tasks in parallel is currently a feasible solution to the performance bottleneck of a single machine. 3-4. Cloud computing is a new type of computing model that appears when traditional standalone technology cannot quickly and accurately complete the ever-increasing data storage and computing requirements. Cloud computing effectively solves the problem of insufficient single machine computing power and limited data storage by building clusters and balancing task load to each computing node in the cluster. 5-6. Therefore, combining cloud computing technology to conduct data mining is a current trend and is of great significance. In recent years, more and more companies have noticed the value of data on the Internet, and using data mining algorithms to dig out useful value from these massive amounts of data has attracted more and more attention from companies. The improvement of traditional mining algorithms and their parallel deployment to the cloud computing environment have attracted many experts and scholars to study. 7-8. Criterion CRETL integrated the Canopy algorithm into the KM TSAR to solve the problem of uncertain K value, and parallelized the improved algorithm based on the Mapreduce programming model, and achieved relatively ideal results. 9. METL used the coarse-grained parallel design idea of GAR algorithm to improve the KM TSAR under Hadoop, avoiding the premature phenomenon of traditional KM. 10. Srinivasulu DLETL parallelized the KM TSAR on the Hadoop cluster, and verified the excellent performance of the parallelized KM TSAR when processing massive data through experiments. 11. This paper conducts a series of tests to verify the performance of the improved CKM parallelization algorithm based on Mapreduce by building a Hadoop platform. Experimental results show that the improved CKM parallelization algorithm is effective and convergent, and can further improve the clustering accuracy and reduce the number of algorithm iterations. 12. 2. Parallel KM TSAR optimization based on optimized parallel design idea of KM in the KM TSAR. There is no dependence on the operations of calculating the distance from all data objects to each centroid. These operations can be performed in parallel and individually, so KM can be transplanted to the Hadoop platform in theory. At the beginning of the algorithm, it is necessary to randomly select K data points in the data set as clustering centers, and then save these cluster centers on HDFS. It will be accessed by the program in the form of global constants. The algorithm will be renewed after each iteration. Generate a set of cluster centers, which are also recorded in HDFS in the form of global constants. The program is designed this way because it needs to compare the gap between the cluster center generated this time and the previous cluster center. If the gap is greater than the given threshold, it will continue to iterate. And if the gap is less than the given threshold, it will be terminated. Each iteration of the algorithm starts a Mapreduce task, which divides the red relatively large data block into many small data blocks according to the needs of the business, and then processes these small data sets in parallel to improve the clustering speed. It is described by Mapreduce as, first, the application in the map phase will read the local original data set, calculate the Euclidean distance of each record to the center of each cluster, and select the cluster with the smallest distance from it as the cluster to which the record belongs. Combiner performs a reduction operation on the local data points that contain the same cluster. The reduce phase will recalculate the new cluster centers of each cluster and write this group of cluster centers into HDFS. Finally, the main function of the entire job will be based on this time. The difference between the cluster center and the last cluster center and the number of iterations of the job are used to determine whether to terminate the program. In the process of processing, the data is communicated and stored in a serialized binary stream, which improves the efficiency of the algorithm. Parallel CKM algorithm optimization strategy. Canopy center point selection optimization. The optimization strategy for the central point selection of the parallel Canopy algorithm is, in the map phase, the area radius T2 is set to the average distance of all data points, and all data points are divided according to this distance. For a huge data set of distributed storage, each node calculate the local Canopy center point in the reduce stage. Since only all local Canopy center points are clustered, the area radius T2 is set to 0.9 times the average distance of all data points, so as to obtain a group of Canopy in the global data space center point. When the data set is particularly large, some data records can be randomly selected to calculate their average distance as the estimate of the area radius T2, so as to reduce the amount of calculation of the estimate while ensuring that the number of samples is sufficient. In addition, as a valuation method, it aims to quickly obtain a more reasonable T2 value. The specific value of T2 may be fine-tuned according to the actual situation. Choosing an appropriate initial cluster center can effectively reduce the number of iterations and improve the accuracy of clustering. KM Iterative Process Optimization. The optimization strategy for the iterative process of the parallelized KM TSA after the Canopy algorithm is used to obtain the KM initial clustering center and the initial Canopy cluster. When calculating the cluster of each data object, there is no need to calculate the data object and all Canopy for the distance of the center point. You only need to calculate the distance between the center point of the Canopy cluster that overlaps it, and then select the Canopy center point with the shortest distance from it as the category cluster, thus saving the high precision distance required for each iteration of KM calculation reduces the time consumed in the overall iterative process. Delete outliers in the data set. Outliers are data objects that are very different from most of the data in the data set. There are many reasons for their occurrence, such as errors in data manipulation, or problems with the original data collected. Therefore, the idea of algorithm improvement is to delete outliers in the data set, or to minimize the influence of outliers on the algorithm. In this paper, the data set to be clustered is cleaned by the Canopy algorithm. If there is only one data object in the generated Canopy cluster, or the cluster contains very few data objects, then the Canopy cluster is considered to be an outlier, and these outliers are considered delete. The number of clusters K is the number of all Canopy clusters, minus the number of isolated Canopy clusters. The initial clustering center of the KM TSA is the center point of the remaining Canopy clusters, so that a more accurate initial cluster center, and the K value of the number of clusters, makes up for the deficiency of the KM TSA. Improved CKM algorithm design based on Hadoop platform. Improved CKM algorithm parallelization design idea. The focus of the Canopy algorithm is how to calculate all Canopy centers. That is, first use the Canopy algorithm to process the original data set to generate a set of cluster centers. Use these data points as the initial cluster centers of KM, and then use KM to compare the original cluster centers. Do more accurate clustering operations on the data set. CKM can effectively prevent the clustering results from falling into a situation where the local effect is good, but the global effect is poor due to the influence of subjective factors, and it can also speed up the clustering process by reducing the number of iterations. Mapreduce Implementation idea. Map phase uses Canopy method to calculate a series of Canopy center points. Since the map process operates on small data sets that are segmented from large data sets, these center points are only local calculation results. Reduce stage will map phase. The output local results are all copied, and the Canopy method is used to calculate the global Canopy center point for these intermediate results again. Mapreduce implementation of the improved CKM algorithm. Canopy center point generation. The Canopy mapper class inherits the mapper class. Here you need to override the map and cleanup methods of the parent class. The role of the map function is to convert the input string into a data object and store it in the data collection list. The cleanup function is the core of this class. The specific process implemented by this method, first arbitrarily select a point from the original data set to form a new Canopy, and delete the point from the original data set among the remaining points in the original data set. If the distance between the data point selected at the beginning is less than T2, remove it from the data set, and assign the data object to the newly formed Canopy. Repeat the process until the original data set is empty. Finally, multiple Canopy class, calculate their Canopy center and output. Here, the value of the area radius T2 is set as the average distance of all data points. The Canopy reducer needs to override the reduce method that is executed multiple times and the cleanup method that is executed only once. The purpose of the reduce method is to obtain the local Canopy center points output by all mappers and store them in the list of data sets to be clustered. The cleanup function of this type is similar to the cleanup function of Canopy mapper, and the distance threshold T2 is set to 0.9 times the average distance of all data points. First, use the Canopy algorithm to divide all data objects to be clustered into suitable Canopy, and then calculate the center point of each Canopy and output it to HDFS. That is, calculate the Canopy center point of the global data space through the input intermediate results. Data object labeling. To label the input data object, this class only needs to implement the mapper class. First, use the setup function to read the file storing the center point of Canopy. The map function reads the input data file line by line, treats each line as a data record, and calculates the distance from the data record to the center point of each Canopy. If the distance is less than T1, then mark the corresponding Canopy cluster to the record, and finally get several Canopy clusters corresponding to each data object. Iteration of KM specific implementation. The map process needs to read the cluster centers obtained in the previous iteration. The input of the map function is offset, data object Canopy list clustered, and each data object is only related to the center of the Canopy cluster that covers it. Point to do distance calculation, select the closest Canopy cluster as the category to which it belongs, and the output format is clustered, data object Canopy list clustered. The reduce process calculates the new cluster centers again, and outputs them to HDFS. The Mapreduce process is repeated until the distance between the new and old cluster centers is less than the threshold, or the maximum number of iterations is reached, and the algorithm is terminated, and then a round of map process is performed to obtain the final clustering result. Algorithm complexity analysis. Using Canopy to optimize it. The initial selection of cluster centers will be more reasonable, which solves the situation that KM often has good local effects but poor global effects, and its number of iterations will be reduced accordingly. It can be seen that the parallelized CKM can further improve the execution speed of KM, especially when the amount of data to be processed increases. Free parallel KM SAR optimization experiment based on experimental environment host planning. Hadoop cluster is built based on several virtual machines in the laboratory LAN environment. In the case of meeting the basic needs of the experiment, in order to save hardware costs, this experiment uses 2 hosts as the host, and installs 2 virtual machines running the CentOS system on each host. The virtual machines are connected by bridge. It is on the same network segment as the host, which ensures that the virtual machine node and the host outside the cluster can communicate with each other. Experimental environment Hadoop cluster planning. Planning the entire Hadoop cluster is actually planning the various components of the platform such as HDFS and YARN. For the underlying HDFS components of the ecosystem, one of the nodes can be selected as the name node to maintain the metadata information corresponding to the cluster system, and all nodes in the cluster can be used as data nodes to provide services for storing data files. For the role planning of the YARN platform, one of the nodes needs to be selected as the resource manager, RM. For the security of the cluster, configure this role to a node different from the name node, and each node in the cluster is managed as a node manager single node resource. Basic principles of KM Criterion function used is as follows. For optimization experiment analysis of parallel KM SAR based on comparison of the accuracy of CKM and the improved CKM algorithm in order to verify the effectiveness of the parallel clustering algorithm. This paper selects iris, standardized seeds, and standardized wine data sets to randomly generate 10 to the power of 4 records each and adds a small amount of noise for testing. The classification results of the original training set are compared with the clustering results of this article, comparing the class results to get the accuracy rate, and judging whether the parallelized algorithm is effective by the accuracy rate. Among them, accuracy refers to the ratio of data points that can be correctly clustered to all data points. The specific results are shown in Table 1. It can be seen from Figure 1 that when processing the iris data set, the number of iterations of the CKM algorithm is more than that of the improved CKM. When processing the seeds data set, CKM and the number of iterations of the improved CKM is relatively small and similar. When processing the wine data set, the number of iterations of the improved CKM is significantly less than that of CKM. The above results show that these 2 parallelized clustering algorithms are both convergent. The improved CKM parallelization algorithm has a faster convergence rate than CKM. This is because the former uses the improved Canopy algorithm. The obtained K initial cluster centers are more reasonable than the latter, and have obvious advantages in the iterative process, which can reduce the number of iterations of the KM SAR to a certain extent. Speed up experiments. Measure the time it takes to run the improved CKM in standalone mode, and gradually increase the number of computing nodes in the cluster to 2, 3, and 4 by modifying the configuration parameters of the Hadoop system. The data used in the experiment are the data sets iris1, iris2, and iris3, and the time consumed by a single iteration is still used as the comparison object, and the improved parallelization algorithm CKM is calculated when processing these data sets. The acceleration ratio changes under the condition that the number of nodes increases from 2 to 4. The experimental results are shown in Figure 2. As can be seen from the above figure, when the improved CKM parallelization algorithm processes the same data set, gradually adding machines in the cluster, the speedup will continue to grow, but the growth rate will gradually shrink. This is due to with the addition of computing nodes, the communication overhead between nodes is gradually increasing, which will consume part of the network resources in the cluster, thereby reducing the growth rate of the acceleration ratio. In the case of the same number of computing nodes, as the scale of the data set continues to expand, the growth trend of the acceleration ratio is also very obvious. It can be seen that the improved CKM parallelization algorithm has a good speedup in a Hadoop cluster. 5 conclusions. Big data technology is a new generation of technology and architecture. that can quickly discover and analyze large-scale data and extract valuable information in an economical way. In the face of various ultra-large-scale data, the standalone processing mode is difficult to meet the actual needs in terms of CPU computing power and disk storage space, and cannot provide processing results within a reasonable time. An excellent solution to this problem is cloud computing technology. Cloud computing technology needs to write parallel programs when processing large-scale data applications, which involves many parallel algorithms. This paper applies the traditional clustering algorithm to the CCPH, and makes full use of the CPU computing power and disk storage performance of a large number of nodes to form a cluster, thereby greatly improving the efficiency of using the clustering algorithm to process huge amounts of data. Thank you.